this lesson is going to focus on two more of our rules for taking derivatives, the product rule and the quotient rule. I do want to point out that a lot of the problems I'm going to do today, for product rule, you probably would not want to use product rule because there's better ways to take the derivative, but we're going to go ahead and look at it so we can get the process of how you use the product rule for a derivative. But again, just to understand, there's probably a quicker way to take most of these derivatives. So product rule is used if you're wanting to take the derivative of two functions being multiplied together. Let's say f of x times g of x. Unlike the quotient or the sum and difference rule, where you just take the derivative of one and then add or subtract it to the derivative of the other, the product rule is a little more difficult. What you're going to do to find the derivative of a function being multiplied with another function is you keep the first function times the derivative of the second plus, then you keep the second function and multiply it by the derivative of the first. Now, a lot of books use, instead of f and g, they'll use u and v to be their two functions. And so they'll write it as u times v prime plus v times u prime. So it's keep one times the derivative of the other, plus, and then just switch that around, the derivative of the first one times keep the second one. Alright, so the way I've set this up is to make a little more sense out of it. A lot of times I'll do it in table form. Let me just go through with one this way, and then we'll look at one that might be in table form. Okay, I think you'll like the tables better. So let's say I wanted to take the derivative of 4x plus 1 times 3x minus 2. So that's two different functions being multiplied together. So we just define one of them, and I'm going to use the uv notation as u and the other one to be the v. Okay. So here's what we're going to do. Remember that it's u times v prime plus v times u prime. Alright, so we keep u first, 4x plus 1, times, then the derivative of v, which would be 3, plus, keep v, 3x minus 2, times the derivative of u, which would be 4. And now we're going to do distributive property, and that's going to give me 12x plus 3 plus 12x minus 8. Now combine like terms, I get 24x minus 5. Now here's what I was talking about when I said there's probably an easier way to do this or a quicker way. I want to go back and look at the original problem. 4x plus 1 times 3x minus 2. And what I'm going to do first is I want to do the multiplication first. Let's FOIL that out. 4x plus 1 times 3x minus 2. So if I do first, I get 12x squared. Let's put outer and inner together. Outer is going to give me minus 8x. Inner is going to give me plus 3x. So that's going to give me minus 5x. And then last is going to give me minus 2. If I FOIL this out first and then take the derivative, notice that I get 24x minus 5, which was the same thing I got up here when I used the product rule. I think you'll agree that it's probably much quicker on problems like this to FOIL them out and then take the derivative. Now again, where this is going to get to be really important is when we start looking at things like, what if I wanted to take the derivative of x squared times, let's say, the sine of x. Well, now I don't have a choice of being able to multiply it out and then trying to take the derivative. There's no FOILing or simplifying I can do with that. Okay, so that's where we're really going to focus on using the product rule, not necessarily with polynomials. I do want to show you how I set it up using table format. It's really the same kind of thing. I think it just makes it a little easier to organize. Let's say, I'm just going to make a new one up. We had 5x squared plus 3x minus 1. And we wanted to multiply that by 2x squared minus 4x plus 3. Now we might agree that this could be a problem, or not a problem, but could be a little time consuming to multiply out. So here's what we do. We assign one of these as u, and one of them is v. So we're going to do u equals, now this time we'll set it up in table form, 5x squared plus 3x minus 1, and v is going to be 2x squared minus 4x plus 3. Then we find u prime and v prime. So if I do u prime, I'm going to get 10x plus 3. V prime is going to be 4x minus 4. And now I do what I call a Jesus fish. Okay? And what you're going to do is you're just going to multiply along those diagonals. And then that's what I'm going to do. I'm going to take u times v prime plus v times u prime. So I would take 5x squared plus 3x minus 1, multiply that by 4x minus 4, and then add 10x plus 3 times 2x squared minus 4x plus 3. Okay. At this point, I'd use distributive property and go ahead and multiply through. Okay, so I went ahead and I just took a minute and multiplied those out, and just to save some time, I multiplied, oops, in the right place. I multiplied 5x squared times negative 4x, and then I multiplied 3x times 4x, negative 1 times 4x, and then I did the reverse. I took 5x times negative 4, 3x times negative 4, negative 1 times negative 4. And then I just went ahead and combined all like terms. And that's how I got these two polynomials. And now what I do is just combine at the end, and I would get 40x cubed. Negative 8x squared and negative 36x squared would be negative 44x squared. Negative 16x and positive 18x would be plus 2x. And then positive 4 and positive 9 would be positive 13. Okay. Once you get used to it, I think you're going to really find that if you'll set these up in table form, they're going to be a whole lot easier to find the derivatives for. Okay. All right. The last thing we're going to look at just quickly is the quotient rule. And quotient rule does the same kind of thing as product rule, in that we're going to make it a u and a v, and I'm just going to go ahead and use it in u-v format. So we're going to think of it as u over v instead of u times v. And the quotient rule goes like this. It's v times u prime minus u times v prime over v squared. Now, to be honest with you, that is not the way I memorized that. I actually have a little mnemonic device I use to help me remember the quotient rule. What we're going to do is we're going to call the top high, and the bottom, normally we call it low, but just because it goes a little easier, we're going to call it ho. So we're going to call it high and ho. Then here's how you're going to remember quotient rule. It goes ho, d high, minus high, d ho, over ho ho. Now, the thing you've got to remember here is that when I put like d high or d ho, what that means is the derivative of. So d high means the derivative of the high, and d ho means the derivative of the ho, or the low, okay? So here's the way you go through this. You just got to remember, it's ho-de high minus hi-de ho over ho-ho. You always start with ho-de high, okay? So let's say I wanted to take the derivative of 4x minus 1 over 2x plus 3. So here's how it's going to go. It's ho, that's the bottom, 2x plus 3, d high, derivative of the top. Derivative of 4x minus 1 would be 4. So ho-de high minus high, 4x minus 1 d ho, derivative of the bottom, 2 over ho, which is really just the bottom squared. The parentheses on this are really important. If you do not put those on there, you're going to end up missing some sign changes and some distributive property. So if I multiply through here, we have 8x plus 12 minus, multiply here, 8x minus 2. But then we can, all over, let's go ahead and put that, 2x plus 3 squared. You never have to worry about expanding this. Okay, so always leave it as ho squared. Okay, so don't expand that. All right, and now we're going to change this minus to plus, and then the opposite. And then what you're going to find a lot of times, so don't panic when it happens, a lot of times what's going to happen here is there's going to be some stuff on the numerator that will cancel out, simplify. Positive 8x and negative 8x will simplify. I will tell you this, rarely are you going to get 0 on the top, so that shouldn't happen. And now I have a positive 12 and a positive 2, so that would give me positive 14 over 2x plus 3 squared. And that's your derivative. Okay, let's try one more of those. Let's say I have, what's the derivative of 6x over 5x minus 1. So to take the derivative, I'm going to do ho high. So it's ho, 5x minus 1, d high, 6, minus high, 6x, d ho, 5. Over ho, 5x minus 1 squared. So if I do distributive property now, I get 30x minus 6 minus 30x over 5x minus 1 squared. We can change that to plus negative. Those cancel. We end up with just negative 6 over 5x minus 1 squared. And that would be your answer. Okay? One of the things you do want to be careful about is you don't want to use ho high with problems that could be done easier, like what we did today. Let's say, let me go ahead and do one of those. Let's say I had something like this. 7x minus 9 over 5. Now you can do this with ho high, but you can actually do it by rewriting it, and I'll do the rewriting here in just a minute. If I look at doing it as a ho high problem, it's going to go like this. Ho, 5. D high, the derivative of 7x minus 9, 7. Minus high, 7x minus 9, d ho. But the derivative of bottom of 5 is 0 over ho. So we end up with, that's going to be 0. 7 times 5 is going to be 35 over 25. But then I can simplify that. Those are both divisible by 5, and I get 7/5. Now if I go back and look at this, I can actually start by rewriting this, because this is linear on the top and you're dividing by a constant. I really could think of this as 7/5 x minus 9/5. This would just make it into two fractions, 7/5 and 9/5. Okay? But then if I write it that way, the derivative of that, of 7/5 x minus 9/5, would just be 7/5. Much easier that way. Okay. You can also do the same thing when you have a constant on the top. I know I've said we're going to wrap up, but this will be our last one. Say I had 4 over 3x cubed. Okay. I can do this as a ho high problem. If I do, it goes ho, 3x cubed, d high, the derivative of 4 will be 0, minus high 4 d ho 9x squared over ho. So it's 3x cubed squared. Now, a lot of you are going to mess up on some of the algebra and simplifying here. This is going to be 0. We're going to have negative 36x squared over, now everything here is going to get squared. 3 squared would be 9. X to the third squared would be x to the 6th. Remember, exponent to exponent, you multiply the exponents. But then that simplifies. 9 goes into 9, 1. It goes into 36, 4. And then x squared and x to the 6 would simplify to give me negative 4 over x to the 4th. Another way I could have looked at that was to rewrite this at the beginning, like we did today, and make that 4/3 x to the negative 3. The derivative of that, negative 3, would multiply with 4/3 and give me negative 4. X to the 1 less power would be negative 4. So I get negative 4 over x to the 4th. So here's the thing. Hody High works for all fractions. When you're doing quotient rule, it's going to work for all your fractions. It's just some fractions are better to not do by Hody High. If your numerator or denominator is just a constant, then try rewriting it because it's probably going to be faster. If you have functions, like we did here, where you've got a 6x and a 5x minus 1, then you're going to want to do it as a Hody High problem. Okay?